What are embeddings? They're the secret behind how artificial intelligence understands meaning. How can numbers capture the essence of words, images, or ideas? How does a machine know that king and queen are related, or that a photo of a dog is similar to another dog? The answer lies in embeddings, a hidden geometric space where meaning has shape, distance, and direction. Let's explore this fascinating world. Let's start with a fundamental question. How can numbers understand words? Words are symbols, abstract concepts created by humans. Computers only understand numbers. So how does artificial intelligence work with language? How does it know that dog relates to puppy, or that happy is the opposite of sad? This is where embeddings come in. They transform words into numbers, but not just any numbers. These numbers capture meaning, relationships, and context. Let's see how. Here's the magic. Each word becomes a point in multidimensional space. Think of it like a map where words with similar meanings are close together. In this simple two-dimensional example, the horizontal axis represents royalty, and the vertical axis represents gender. King and man are high on the gender scale, but king and queen are both high on royalty. Prince and princess sit in between. The position of each point captures its meaning. Similar words become close points in space. This is the foundation of embeddings. Welcome to vector space, the hidden dimension of meaning. Think of embeddings as coordinates in a multidimensional map. Each word has a position defined by hundreds of numbers. We can only visualize 3 dimensions, but real embeddings live in much higher dimensional spaces. Word2Vec uses 300 dimensions. Modern language models like GPT used 768 to over 12,000 dimensions. Each dimension captures a different aspect of meaning. Animals cluster together. Vehicles group in their own region. Emotions form their own neighborhood. In this vast space, meaning has geometry. Distance matters. Direction matters. And the math works beautifully. In embedding space, similarity equals distance. Words with similar meanings cluster together, forming tight neighborhoods. Dog and cat are close because they're both animals. Puppy and kitten are nearby too. Food words like pizza, burger, and pasta form their own cluster far from animals. And outliers like quantum sit alone, distant from everyday words. The distance between points directly measures how different the meanings are. Short distance means high similarity. Long distance means low similarity. This simple geometric principle powers recommendation systems. It's elegant mathematics underlying artificial intelligence. Let's see the math behind embeddings. Don't worry, it's beautiful. Each word becomes a d-dimensional vector. Cosine similarity measures how aligned 2 vectors are. It computes the cosine of the angle between them. Euclidean distance measures straight line difference between vectors. Word2Vec's training objective predicts context words from the center word. Through these equations, embeddings learn the geometry of meaning. It learns not by memorizing, but by arranging words so the math works out perfectly. Now for the magic. Vector arithmetic. The most famous example is king minus man plus woman, approximately equals queen. This isn't a trick. It's geometry. Start with the king vector. Subtract the concept of male by removing the man vector. Then, add the concept of female by adding the woman vector. The result lands incredibly close to queen. Why does this work? Because embeddings capture semantic relationships as geometric patterns. The direction from man to woman represents gender. The direction from man to king represents royalty. These relationships are consistent across the space. You can do walked minus walk plus run to get running, or Paris minus France plus Italy to get Rome. It's linear algebra meeting meaning. Mathematics captures concept. Embeddings automatically organize knowledge into clusters. Animal words group together. Dog, cat. Emotion words form their own neighborhood. Happy, joyful, sad, angry. Colors cluster. Red, blue, green, yellow, purple. Numbers gather. 1, 2, 3, 10, 100. No one programs these groups explicitly. They emerge naturally from learning patterns in text. Words that appear in similar contexts end up close in embedding space. This is unsupervised learning at its finest. A model discovers structure in language without being told. It learns that animals behave similarly. Emotions express feelings. Colors describe appearance. Numbers indicate quantity. Knowledge self-organizes into a beautiful geometric structure. What do these hundreds of dimensions actually represent? Each dimension captures a different aspect of meaning. One dimension might encode animacy, is something alive or inanimate. Another might represent size, small to large. A third could capture emotional valence, negative to positive. Others encode abstractness, time intensity, and countless other patterns. The beautiful part: these aren't handcrafted features. AI discovers them automatically by learning from data. No human programs what dimension 47 should mean. The model learns that certain patterns are useful for prediction. Together, these hundreds of dimensions form a rich representation that captures nuanced meaning. It's emergent intelligence from mathematical optimization. How do embeddings learn? The key insight is context. Words that appear in similar contexts should have similar meanings. Consider the cat sat on the mat. To predict cat, the model looks at surrounding words, the sat on mat. Now imagine thousands of sentences with dog. The dog sat on the rug. A dog ran in the park. Cat and dog appear in similar contexts, so they should have similar embeddings. Different training methods exist. Wartwavik from 2013 predicts words from context. Glove from 2014 learns from word co-occurrence statistics. Modern transformers from 2017 onward create deep contextual embeddings. But through massive amounts of text and mathematical optimization, embeddings learn the geometry of meaning. Embeddings aren't just for words. The same principle works for anything. Images get embeddings where similar pictures cluster together. Models like Clip and ResNet convert photos into vectors. Audio embeddings group similar sounds. While 2Vic and Jukebox understand music and speech. Code gets embeddings too. CodeBERT and CodeT5 put similar functions near each other in space. Even molecules have embeddings. ChemBERT learns chemical structure. User preferences become vectors for recommendations. Products get embeddings for Amazon and Netflix. The universal principle: convert things to vectors where similar things have similar vectors. This unlocks search, recommendation, clustering, and comparison. It's a fundamental tool across all of AI. Once you have embeddings, you have geometry. And geometry gives you structure. Embeddings power virtually every modern AI system. Search engines use them for semantic search, finding documents by meaning rather than just keywords. Recommendation systems at Netflix, Spotify, and Amazon use embeddings to find similar items you might like. Chatbots like ChatGPT and Claude use embeddings to understand your queries. Google Translate uses multilingual embeddings where different languages share the same space. Clustering algorithms group similar items automatically. Image search finds visually similar pictures. Voice assistants like Alexa and Siri embed speech for understanding. Text classification for spam detection and sentiment analysis relies on embeddings. Even drug discovery uses molecular embeddings to find similar compounds. Embeddings are everywhere in modern AI. They are the hidden layer that makes intelligence possible. By converting everything to vectors, we unlock the power of geometry and mathematics to understand meaning. Embeddings are pure magic. They transform abstract concepts into concrete mathematics. Numbers capture meaning through geometry. Similar things become similar vectors. Distance measures semantic similarity. Vector arithmetic lets us compute with concepts. King minus man plus woman gives us queen. And embeddings work for everything. Words, images, audio, code, molecules, users, products. They power search engines, recommendations, chatbots, translation, and countless other applications. Embeddings are the secret language of artificial intelligence. They're how machines understand our world. By converting everything to vectors, AI can compare, search, cluster, and reason about meaning. It's beautiful mathematics meeting human language. The hidden geometry of meaning now revealed. Thank you for watching. You now understand embeddings, the hidden geometry of meaning. You've seen how numbers capture concepts, how distance measures similarity, and how this powers modern AI. Next time you use a search engine, get a recommendation, or chat with AI, remember embeddings are working behind the scenes, organizing knowledge in beautiful high-dimensional spaces. Keep exploring. Don't forget to like and subscribe.